Okay, so this is lecture number 4 in my series on algebraic number theory, and I want to talk about all things Noetherian. So in particular, I want to talk about Noetherian rings and Noetherian modules in this lecture. So first, we'll start with Noetherian rings. So first we should define what a Noetherian ring is. Definition. A ring A is Noetherian if every ideal in A is finally generated. Okay, so this may not be the definition of Noetherian that you've seen, but it's certainly equivalent to any other definition of Noetherian you've seen. And most of the rings, it turns out, most of the rings that I'm interested in, almost all the rings are Noetherian. It's not true that every ring that a number theorist might want to study is Noetherian, but it certainly makes up a large class of rings. Okay, so the first proposition, which is probably this is always the first thing you prove about Noetherian rings, is the equivalence of the following conditions on A. So the following are equivalent conditions on a ring A. The first is A is Noetherian, i.e. every ideal is finally generated. The second is every ascending chain of ideals stabilizes we'll refer to this as the ascending chain condition, or ACC for short. And 3, probably one that you maybe have seen a little bit less of. Every non-empty set S of ideals in A has a maximal element. What I mean when I say a maximal element here, I mean with respect to inclusion. Okay. So let's go ahead and prove this proposition. How are we going to do this? Well, we're going to do it probably the easiest way. We're going to show 1 implies 2, which implies 3, which implies 1. Okay, so first, I guess throughout the whole thing we're going to let A be a ring. First, assume A is Noetherian, i.e. every ideal of A is finitely generated. Okay, so we need to show that every ascending chain of ideals stabilizes, so we're going to start with an ascending chain of ideals. Let A1, A2, so on and so forth be an ascending chain of ideals. how do I show this thing stabilizes? The idea is to essentially define some big ideal, choose a finite list of generators, and then this finite list of generators is going to somehow determine where this chain stabilizes. So we're going to let A be the set, the union over M at least one of these A sub M's. Since this thing is a chain, you can easily check that this big A, or this A, which is the union of these guys, is an ideal. Since A1 is contained in A2, and so on and so forth, A is an ideal. Okay. By the Noetherian hypothesis, it has a finite list of generators. Choose generators. Little a1 through little an. Okay. And essentially the idea is wherever the last AI occurs, that's when your chain stabilizes. Okay, so we're going to let's say A sub j is in A sub sigma of j, and choose big N so that A1, I guess, yeah, maybe I didn't have to state this. Maybe I can just say this. Choose big N so that A1 through AN all live in A sub N. Okay, we can find this because each AI lives in some A sub M, so you can just choose the biggest one, and it'll contain all of these. Okay, I claim A sub M equals A sub N for n bigger than N. We have one containment already, so we really just need to show that A sub M is contained in A sub M. We're going to let A be in A sub M. Then, right, A is going to be in this big union ideal, so A equals the sum of C sub I, A sub I for some C sub I in A. Then we see immediately that A is in A sub N, since each A sub I is in A sub N. Okay, and this thing is an ideal. Okay, so this proves 1 implies 2. Okay, now let's show 2 implies 3. So now assume A satisfies the ascending chain condition. Okay, so we're going to let S be a non-empty set of ideals, and we're going to use Zorn's lemma basically to prove the proposition. Let S be a non-empty set of ideals. We put a partial order on S by inclusion. Okay. And once we've done this, the ascending chain condition is going to essentially tell us that every chain, let me be precise in how I want to state this here. The ascending chain condition immediately implies that every chain has an upper bound in S, since this is a non-empty partially ordered set in which every chain has an upper bound, S necessarily has a maximal element with respect to our partial order, which is inclusion. By Zorn's lemma, S has a maximal element. Okay, with respect to inclusion. Thus, 2 implies 3. Finally, we have to show that 3 implies 2. Or, sorry, 3 implies 1. Okay. Suppose every non-empty set of ideals in A has a maximal element we need to show that every ideal is finitely generated, so we're going to let A, subset of A, be an ideal, and we're going to let S, so to apply this thing we need a non-empty set of ideals. We're going to let S be the set of all finitely generated subideals of A. I subset of A, such that I is finitely generated. So notice that this set is non-empty. We can always take I to be the 0 ideal. S is non-empty, so it has a maximal element. Let's say I. We're going to let A be an A. Or sorry, I don't want the whole ring A. I want the ideal math frac A. A being my ideal A. No. Since I is finitely generated, the sum of these two ideals is finitely generated and contained in my ideal A. So this thing is an element of S. Furthermore, I is contained in the sum of these two ideals. So by maximality of I in S, I equals I plus A, and A is necessarily an I. Thus, I has to equal my ideal math frac A, and A, I equals A, is finitely generated. So, since S only consisted of finitely generated subideals of A, and A is in S, A necessarily has to be finitely generated. Okay, so this finishes the equivalence of all these definitions of Noetherian. Okay. Noetherian is basically something called a finite condition that people put on rings, and essentially, like, putting conditions like Noetherian on your ring helps you not look at pathological examples of rings. Okay. Unless that's your thing, in which case you may not want to assume your rings are Noetherian. But for most of algebraic geometry and algebraic number theory, many of your rings are going to be Noetherian. Okay. So what other properties do Noetherian rings have? The following proposition is a slight variant on. It's like as close as you can get to unique factorization for just Noetherian domains. Okay, so the following proposition: every non-zero, non-unit in a Noetherian integral domain can be written, not necessarily uniquely, as a product of irreducible elements. Okay, so what this says is I can, in Noetherian integral domains, I can break up my elements into irreducible elements. Okay, not necessarily uniquely again, but I can still break it into a product of irreducibles. So, proof. We're going to let A be a Noetherian integral domain. Okay, and we're going to see here. We're going to let S be the set of ideals, cyclic ideals, generated by elements A, such that A cannot be written as a product of irreducible elements. And we're going to assume, for the sake of contradiction, that S is non-empty. And since A is Noetherian, condition 3 of our equivalent conditions on a ring being Noetherian means that we can find a maximal element of S. Let A be an S, be a maximal element of S, and A is going to be this element with A not a product of irreducibles. In particular, A itself is not irreducible, because then it would be trivial. It would just be like a single element, a single irreducible element is trivially a product of irreducibles. It's just that element times 1 or something like we consider just a single element to be a product, I guess, is maybe the the formal thing that's going on here. In particular, A is not irreducible. Just like how when you're talking about factorization into primes, a single prime factors as just itself. Okay, so since this element A is not irreducible, we can write A as a product of two non-zero non-units. Since A is not irreducible, A equals B times C for non-zero non-units. B and C. Right. Okay. So this is just the definition of what it means to not be irreducible. If B and C were both the product of irreducibles, then A would be we could just concatenate the two products. So one of B or C has to not be a product of irreducibles. We're going to assume that it's B just by symmetry. By symmetry, we can assume B is not a product of irreducibles. So notice basically A is in the ideal generated by B. So A is contained in this ideal. However, A is maximal in this set S. B is also in this set S because B cannot be written as a product of irreducibles. It's a non-zero non-unit which cannot be written as a product of irreducibles. So that by the maximality of A, or by the maximality of this ideal generated by A, we have to have the ideal generated by A is equal to the ideal generated by B. Thus, so if B is in this ideal generated by A, then we can find some D so that AD equals B. Then, well, if I multiply through my equation up here by D, I'm going to get B equals AD equals DBC. Since B is a non-zero non-unit, well, really just non-zero, and A is an integral domain, I can use my cancellation property of being an integral domain to get that 1 is going to be equal to D times C. Thus, C is a unit. However, at the very beginning, we assumed that both B and C were non-units because this element A was irreducible. This is a contradiction. Thus, S has to be empty, and the result follows. Okay. Okay, so this is a nice property of Noetherian integral domains. You can break down elements into products of irreducibles. Okay. So at this point I want to switch from talking about Noetherian rings to focusing more on Noetherian modules. Okay, so remember an R module is essentially like a vector space, but not over a field, over a ring. So let's talk about Noetherian modules. Okay. And again, first I should tell you what a Noetherian module is. Let A be a ring. And A module M. And I guess a small remark here. Since our rings are always going to be commutative with unit, I don't need to worry about whether I have a left or a right or a bi module. Everything, like, until I run into a non-commutative ring, I'm not going to worry about left, right, or bi. Okay. M and A module M is said to be Noetherian if instead of every ideal, every submodule is finitely generated. Okay. Here's a proposition replicating that of Noetherian rings. The following conditions on an A module are equivalent. Okay, 1. M is Noetherian. 2. Every ascending chain of submodules stabilizes. And 3. Every non-empty set of submodules has a maximal element. Okay, and if you want to prove this, just go through my proof of the ring case and replace every time I say ideal with submodule, basically. Okay. Okay. So, how do I guess maybe some questions is like, how do I determine if my submodule, or if my module M is Noetherian? The first proposition is basically tells you if you are an extension of Noetherian modules, then you're also Noetherian. So let M be an A module. Yeah. Let M be an A module. And let M be a submodule. If N and M mod N are both Noetherian, then so is M. Okay. And the proof looks something like this. Proof: let N subset of M be A modules you can choose generators. Choose generators. Let's say y1 through yk for n as a submodule, or as an A module. So I choose generators for n, and let's say x1 through xl for m mod n. And then if you just choose lifts of these guys together with these y's, those will generate m. Then if xi in m is a lift of m mod n, then the collection y1 through yk, x1 through xl will generate m. Okay, and this isn't too hard to prove. I'm not going to go through all the details. You could just take an element m. I'll just say in words very briefly. Take a little m here. Subtract off. When I take a little m here, look at m bar. Write it as a linear combination of these xi bars. The difference upstairs is going to live in n, and thus can be written as a combination of these yi's. Okay, so that's how you would finish the proof. Okay, and the principal application of this, I guess one remark I want to make. The condition of A being a Noetherian ring, note that A is a Noetherian ring if and only if the left regular module, the left regular module, so A regarded as an A module, is a Noetherian module. And this is exactly because ideals of A are precisely submodules of the left regular module. Okay. So the following proposition is the application of this guy here. What does it say? It says let A be a Noetherian ring then every finitely generated A module is also Noetherian. And the proof is a proof by induction. Proof. First, we show the result when M is cyclic, when M is generated by a single element. We show the result M is cyclic. Okay, so we're going to let M be equal to M generated by little m. We can define a map pi from A to M, which sends a little a maps to little a times m. And notice that this map will be a surjection. Define pi, which will be a surjection. That's exactly what it means for little m to generate big M. Okay, so this map here is this projection. You can let's just say n is a submodule of M. The preimage pi inverse of n subset of A will be an ideal. You can check this directly. Choose generators. A1 through AN. Since A is Noetherian, there are finitely many of these. And pi of A1 through pi of AN will generate N. Okay, so thus every submodule of M is finitely generated, so that M is a Noetherian A module. Okay, now we need to do the induction step. Suppose we know the result. When M is generated by N, at least one element. Let's consider M, which is generated by M plus 1 elements. Okay. We're going to let N, this is just going to be the submodule generated by a single element. By our base case, N is Noetherian. If you look at the quotient M mod N, this will be generated by little n elements. M mod N is generated Okay, we seem to have had some technical difficulties, but I think I fixed it. The quotient M mod M is generated by M1 bar through Mn bar. There are images in the quotient. So by our induction hypothesis, M mod N is Noetherian. And thus, by our previous proposition, M is also Noetherian. So we found a submodule so that basically we showed M is an extension of a Noetherian module by a Noetherian module. So M is Noetherian as well. By induction, any finitely generated module is Noetherian, so the result follows by induction. Okay, so this is a useful this is a useful proposition because it kind of from a Noetherian ring you get many Noetherian modules. Any finitely generated module will be Noetherian, which is useful to know. Okay, so this is pretty much where I want to stop for this lecture. This is the bulk of what I'm going to need about Noetherian rings and modules, where we'll continue on with the preliminaries from commutative algebra. But, yeah, okay.